So here's a pretty straightforward integral. If you're using the formulas that I've just put into the notes here for, or a couple new integration formulas using the derivatives that we found in the previous section, then this is a pretty simple problem. And I guess here I'll go ahead and acknowledge that formula. So there's a formula I've provided that says an integral of the form 1 over a squared plus u squared du is equal to 1 over a. And this is, by the way, it's important to distinguish when you're using this formula that a is some number, u is some differentiable function of x. So a is always going to refer to the constant term. So in this case, a squared is 9 and a is 3 in the case of this integral over here. But an integral of this form has an antiderivative 1 over a times inverse tangent of u over a plus c. So using that formula, evaluating this integral is straightforward. It's a one-step problem. We would just want to note that, okay, so if a squared is equal to 9, then a is 3. If u squared is equal to x squared, then u is equal to x, which means du is just equal to 1 times dx. So this has exactly the form 1 over, well, here's your a squared plus u squared. It's addition, so the order doesn't matter, times du. And so the antiderivative is 1 over a times inverse tangent of u over a plus c. So, I mean, there's the answer. There's no work that needs to be shown in this problem. But I wanted to work through, say we didn't have that formula, just to, as a way of sort of verifying that formula over there. What if we wanted to show all the steps? So I'm going to go back to the original question here. So if we want to just purely work from the fact that, okay, this happens to look a lot like the derivative of inverse tangent or arctangent of x, which is 1 over 1 plus x squared. Right? We differentiated that in the previous section. Except we don't have 1 over 1 plus x squared. We have 1 over 9 plus x squared. So if I want to make this integrand here look more like that exact derivative, I could factor out 9 in the denominator. Now I know this is something that you may not be used to, factoring out 9 when 9 is not a factor of this x squared term here. It can be done though. So the idea here, if you factor out 9, then when you're trying to decide what's left, if I pull out a 9, I mean, from the 9 here, of course, it's just a 1. And the reason we know it's 1 is because what you're really doing is taking 9 divided by 9 is 1. So to figure out what's left in this position here, you could do the same thing, divide by 9. So this will be x squared over 9. Notice that if I distribute the 9 here, so 9 times x squared over 9, that's just x squared plus 9. It's equal, if you distribute the 9, you're right back here with the original expression. Okay, so I want to do that in the denominator. Let's say we factor out that 9, and so I divide both parts here. So x squared divided by 9 plus 9 divided by 9, which is 1, dx. And then now, 1 over 9 is now a constant coefficient, so I could move that out in front of the integral. And I'm going to rewrite this x squared over 9 as, let me get another color here, x over 3 all squared plus 1. So now this is looking even closer to this format here for the derivative of inverse tangent. If I do a u substitution now, where u is equal to, suppose I decide I'm going to let u equal x over 3. Then du, so keep in mind x over 3, that can be written as 1/3 times x. The derivative is 1/3 dx. So suppose now, so we've got this 1/9, and then 1 over, so I'm going to make this x over 3 squared plus 1. Okay, with u substitutions, all I need is a multiple, a constant multiple of what I already have in the integral, then what I like to do is just go ahead and multiply by that. So go ahead and multiply by 1/3 here, so that I have this now is equal to du. And that's fine as long as I multiply by the reciprocal out front. So if I multiply by 3 out here, because notice if I bump this 1/3 out front, I'll have 3/3, which is 1. So I haven't changed the quantity in that integral. And the x/3 here is u. So now, here, 1/9 times 3, so that's 1/3. And now this integral has the form 1 over x/3 is equal to u, so this is u squared plus 1. 1/3 dx is equal to du. So now this is exactly the derivative of inverse tangent. And so the antiderivative is, sorry to use the bottom of the board here, but it's inverse tangent of u. Which I'll put in red here, plus c. And we've got that 1/3 out front still. Is that visible? Yeah. So 1/3 inverse tangent of u, which is x/3. So there's your answer. 1/3, maybe just point to this, 1/3 inverse tangent of x/3 plus c as our answer. I wanted to show you how to work this out algebraically, just so we're not blindly, I don't really want you guys to have to blindly trust a formula that I provide. And since I didn't prove them, although you can derive these integration formulas, like this one, and then the arc sine, the arc secant one, by taking this kind of approach. And I'll make that one last thing in this video. If we did want to actually, derive this integration formula from scratch, what we would do, so let's say we have u squared plus a squared du. Factor out, we want to make it look like 1 over u squared plus 1. So factor out a squared in the denominator here. So if we factor out a squared, we'll have u squared divided by a squared plus 1. A squared divided by a squared du. You move this 1 over a squared out front, and I may not work out the rest of this. This u squared over a squared, if we write this as u over a all squared, and now you would do the substitution. Instead of u equals x/3, we'll have, I guess I shouldn't use u because u is kind of representing something different here. But let's say t equals u over a. Then dt is 1 over a du. And so this, you're going to need that 1 over a here, multiply by a out here. Maybe you can see how the rest of this will flow. But then you'll arrive at this as your final answer if you want to work out the details of that.